So in this video looking at AS statistics, we'll be focusing on probability and with the emphasis of discrete random variables. Now this topic, depending on your syllabus, might be as a standalone topic or might be included in the probability section. So as mentioned, this particular topic of discrete random variables may be included as a standalone topic on your AS syllabus, or it might be included in the probability section. So before we go on here, let's have a look at what the actual definition of a discrete random variable is. So a random variable x is a variable that represents the value obtained when we take a measurement from an experiment in the real world. Now, discrete random variable is where a random variable must take a specific numerical value within a given range and where the probability of an event within its experiment is fixed. Now that might sound like a bit of a mouthful, but trust me, when we go through examples it will make perfect sense. Now, another thing is that particularly with the A level and the AS exam, is notation is really key, and presentation of how you're writing down are going to be key things, and also maximizes your marks when you're going through mark schemes or when you're going through test papers. So a capital letter such as X is used as a label for the random variable. The lowercase letter such as X is used to represent a particular value of X. Now the probability that x takes a particular value is written as Px equals x, or just P of x, and this is known as the probability density function, or PDF. If x is a discrete random variable with probability function P of x, then the sum of P of x must equal 1, and the probability distribution of x is given by a set of all possible values together with the values of P of x, and this is usually in the form of a table whereby the sum of P of x equals 1. Now again, that may just sound like absolute gibberish, but like I said, when you go through, actually from on the onset, that might seem very confusing, but when we go through examples I will go through what each of those particular bullet points actually represent. But definitely in terms of your notes, I would definitely make a note of the definition, because there are other random variable tests that you can work with, particularly that's linked in with A-level statistics. You can also get continuous random variables, but with the syllabus that majority you will be doing, you tend to be focusing on discrete random variables, and the notation is something that's definitely worth making note of. But like I said, on face value it might seem absolute nonsense, but when we go through some examples I'll try and refer back and explain what each of those things mean. Now in terms of an example, so let's have a look at the first one. So here we've got number 1. So a child's pocket money is decided by the roll of a die and can be represented as a discrete random variable m. Draw the probability function of m. Now I'm just going to change the wording of that, because that should be probability density function of m. Now basically what this means is, if we have a look now in terms of values on the die, now the probability function density is creating like a function whereby we're representing what the probabilities are for each of the possible values of x, or m in this case. So what we're working out with A is we want to work out the probability that m, which is the experiment, and little m are the possible values that capital M can take. So for example, if I just do this and again, so the possible values that little m can take are 1, 2, 3, 4, 5 and 6, and the probability of getting all of those values, because as it's a normal regular die, is going to be 1/6. So this is the probability that we can use when m equals these values. Now when you are doing a PDF, or when you're representing things like this, what you also need to represent is for other values. So it's a bit like a sample space diagram, where you've got to kind of specify that you've included all for all other values. Now on a die, the only numbers you can get are going to be 1 to 6. So the probability of you getting a 0 or a minus number or a 7 or a 10 is therefore going to be 0. And that there, what we have done is we've created our PDF. Now the next thing we then need to do is draw our probability distribution, which is again just a way of representing the probabilities in the form of a table. So here we've got little m, and we know that we can get the values of 1, 2, 3, 4, 5 and 6, and the probabilities that m equals little m is going to be a 6 if it's 1, it's a 6 to get a 2, a 6 to get a 3, a 6 to get a 4, a 6 to get a 5 and a 6 to get a 6. Now if I just carefully tend to convert that into a table, there what I've done is I've drawn my probability distribution. So function is where you're kind of like writing it as a function, making sure that you've included all possible values, and probability distribution is where you're linking it into a table. So here what we're doing is writing as a function, and a distribution is where you're drawing a table. Now, one of the most important properties of a probability distribution, and this is really key, is that all of these probabilities has to add up to 1. So whenever you are thinking of a probability, or you're asked to draw anything that's related to a probability distribution, the key thing you need to remember is that all of these need to add up to 1. And how that was written in the notation is the sum of, let me just get rid of that. So the sum of P of M, it could be any letter, equals all the values of M is got to equal 1. So the sum of all of those must all add up to 1. So again, you could get questions that are asked related to these. So for example, you could get asked what's the probability of getting a number between or what's the probability of the child getting between £3 and £5, and then you could work it out in terms of inequalities. Now if you were to ask, and again the key thing to remember here is that you can get decimal numbers, but again it needs to be sort of identified and sort of written at the start of a question. So in our second example, the question says the PDF of a discrete random variable y is given by P of y equals cy squared for y equals 0, 1, 2, 3 and 4. Given that c is a constant, find the value of c. So first things first, what we need to do is we've been given the probability function. Now again, this is not really necessary, but just to make it of what we're actually doing, which clearly looks like I don't know what I'm doing. So let's have a look. So here we've got the probability that y equals y, and what we've got is we've got a formula which is cy squared, and the possible values of y equals 1, 0, 1, 2, 3 and 4. And it's 0 for all other values that y could possibly be. Now this is not essential because it's the PDF, but it's just written in this form. Now typically in textbooks you might find that your PDF will be written like this, simply because it's quite complicated to represent your probability function like, let me just get another pen, like this on paper when you're typing it up on a computer. So what they'll generally do is write your PDF like this, but the correct way of doing it is by writing like it, like you can see on the board, on the screen, sorry. So first things first, let's draw our table. So from this we've got that y can equal 0, 1, 2, 3 and 4, and I want to work out the probability using the probability function that y equals y. Again, I'm going to set up my table like so. So from this, what we're then going to do, and I'm just complete the table like so. So what we're going to do is we're going to substitute the y values. So in the probabilities, to work out the probabilities, what I need to use is use the respective values of y. So I'm going to substitute the y values in my table into this function here to find out what the probabilities are. So here I'm going to have 0 squared c, so that's just 0, 1 squared c, so that's just 1c, 2 squared, which is 4, so that's 4c, 3 squared is 9, so that's 9c, and 4 squared, which is 16c, like so. Now as I said, one of the key principles of a probability distribution is that the probabilities must add up to 1. So all of these values, so the sum of y equals y, again I've done that wrong, so the sum of the probabilities of y equals y must equal 1. So therefore 1c plus 4c plus 9c plus 16c must equal 1. So from that, if I then join these together, so I've got 5, 14, so I've got 30c equals 1, so therefore c equals 1 over 30. Now once I've figured out that c equals 1 over 30, what I've now got to do, well, I can actually, I've actually answered the question because it's told me what c is. Now if I was to then go on to answer any particular questions of related to this probability distribution, then what I would then simply do is substitute c into the table. So 0 stays the same, so let me just put that in brackets. This is therefore going to be 1 over 30. This is going to be 4 over 30. This is going to be 9 over 30. And this is going to be 16 over 30. Now one thing you can do is go on to simplify the fractions or the probabilities, but I personally would leave it as it is, and when you come to working with the questions, so for example if a question asked you what's the probability of getting 2 or less, then your probability would be 5 over 30, and then you simplify that final answer. In terms of probabilities in your table, I would leave it unsimplified just so it's easy for you to check and stop you from making any silly mistakes when it comes to combining the probabilities together. So let's have a look at another example. So here we've got a discrete random variable r has a probability density function, and here we've got our function. So the question is asking us first to find the constant of c. So here we've got our function. So first thing I'm going to do is create a table. Now we know that the possible values are 0, 1, 2 and 3. So I'm going to write r, and I've got 0, 1, 2 and 3. And again I'm going to create that table. And the probability that r equals little r is as follows. So now what I'm going to do is I'm going to substitute these numbers into this formula to work out what the respective values are going to be. So here I've got 3 take away 0, where r is the value above in the column. So 3 take away 0 is 3, and so it's just 3c. 3 take away 1 is 2, so that's 2c. 3 take away 2 is 1, so that's just 1c. And 3 take away 3 is 0, so it's 0c. And so there I've got my probability distribution function, or distribution I have to say. So next thing I've now got to do is work out the actual probability. I need to find out the value of c. So again, the key property is that each of these probabilities has got to add up to 1. So here what I've got is I've got 3c plus 2c plus 1c equals 1. And again, what I've used is the sum that of the probability that r equals r has got to equal 1. And so what we've got is I've got 6c equals 1, so therefore c equals 1/6. So again, what I'm now going to do is I'm going to draw the table again. And again, it's not really essential, but sometimes it's better because I'm going to need it to work out the following values and the probability that r equals r. So here I'm going to have 3/6, and again all I'm doing is substituting c equals 1/6 into each of these, and then I've got 2/6, I've got 1/6, and I've got a 0. So working out a, so this is my value of answer to a. So b, what I want to do is work out the probability that r is greater or equal to 1 but less than 3. So what that means is I'm going to be looking at these two probabilities here. Now if I was to then go on to simplify this as 1/3, which I could have done, again it just makes it a lot easier for me to work with these two fractions. Because the denominators are the same, I'm just simply adding them up. It's going to be 3/6, which then simplifies to give me a half, and there is your final answer. So that's why it's easy. I don't need to, let's say, simplify the fractions in my table, but certainly do need to simplify my fractions in my final answers. So let's just have a look at the final answer. Again, I'm just make a quick edit on that. So here we've got two tetrahedral die. Each faces labelled 1, 2, 3 and 4 are thrown, and the scores are noted where the score is the sum of the two numbers on which the dice land. Find the probability density function of x, where x is a random variable, and the score when the two dice are thrown. So here what we're trying to do is we're trying to find the probability density function not the probability distribution. So here what we can do is, well, first things first, what we need to do is find out what the possible values we can get. So if I quickly do a sample space diagram of the two die that are being thrown, and I just click, so here we've got 2, 3, 4, 5, 6, 5, 4, 3, 4, 5, 6, 7, 5, 6, 7, 8. So here you can see in terms of the range of values that x can be, so here I've got x equals, and it's going to be 2, 3, 4, 5, 6, 7 and 8. And I've got probability that x equals x there. So converting the sample space, looking at the sample space diagram, what I'm now going to do is have a look at what the probabilities are for these respective x values. So this here is going to be 1 over 16, because I've got 16 possible values. 3 is going to be 2 over 16. 4 is 3 over 16. 5, which is the most common one, is 4 over 16. 6 is 3 over 16. 7 is 2 over 16. And 8 is 1 over 16. Now, one thing that, again, taking your knowledge of DRVs a little bit sort of further, is I can see that this is what we call a symmetrical distribution, because here you can see from the peak, which are 5, which is our middle value, the probabilities are mirrored between the values of x, and this is what we call a symmetrical distribution. So we've not finished, because again we've done our probability distribution, but we've not done our probability density function. Now again, this is a key area of why you do not simplify the values, or you'll simplify your fractions in your table. Now from the probability distribution table, we can notice that the pattern for probabilities relating to x from 2 to 5 can actually be represented. So if I'm just looking at these values here, I notice that the probability that x equals x can be represented, and these values are 1 less than the x values. So here I've got x minus 1 over 16, and that's for values of x where x is between 2, 3, 4 and 5. Now for the probability of x equals x between x equals 6, 7 and 8, now what I then need to do is find a common, if you think about sequences, I need to find a value or a formula that links the x values of 6, 7, 8 to the numbers of 3, 2 and 1. And how we do that is that's simply going to be 9 take away x equals 16, over 16 rather. And here what I've now got is a formula that allows me to substitute these values of x and find the respective probabilities. So writing the final answer to this particular question, which I'll do in a different colour, let's go for blue. So in terms of the PDF, it's going to be that p of x equals little x. Now here we've got x minus 1 over 16, and that's for where x is between 2, 3, 4 and 5. We've then got a formula of x, 9 minus x over 16, and that's for values of 6, 7 and 8. Now one thing that a lot of students tend to forget is we then need to write 0, and that's for all other values of x. And you might see that bottom line as being kind of useless, but it's something that you kind of need to sort of relate to, as just by saying that there are no other possible values that x can be, and if they were to be a value that's outside of that given range, then the probability of getting such values would be 0. So for example, if you got x equals 1 or x equals 10 or x equals 12, probability is 0. And again, it's kind of just stating the obvious.